A 4 nanocoulomb point charge is placed on the y-axis at y equals 5. Okay, all right, this will be 4 nanocoulombs at 5, okay? And a negative 4 Newton coulombs is placed on the y-axis at negative 5, okay? So that works. So this will be 5. This will be negative 5. And this will also be a negative 4 nanocoulombs. Okay. What is the magnitude of the electric field at the point in the x-axis where x equals 3 centimeters? These are all in centimeters. So this will be 3 centimeters. And we want to find out the electric field here. Okay, so first way to think of electric fields is positives are sources and negatives are sinks. I like to think of this kind of as like a water. So if you have like a faucet with water, kind of like so, and it's positive, then water's coming out. Negative, it's a sink at the bottom, it's going in. And so this is how I draw the electric field lines, like so. So where it goes, electric field lines go into a sink and out of a source. So what's going to happen here then is there's going to be electric field lines that's radiating out radially from this 4 nanocoulomb. I'm going to redraw this just so that I get a better sense of proportion here. I'm going to exaggerate it too. That way it'll make it easier for my directions to make sense. Or, yeah, directions. So this will be 3, this will be 5. And so this source is going to come down this way and create an electric field line going that direction. It's also doing it in every direction, like so, but we don't care about those directions. We're only concerned in the direction that has to do with 3 centimeters. And then this one right here is going to have an electric field going, no, not quite, kind of like so, like this electric field going that way. And so when these add up together, since you can tell they're both symmetrical, you have 5 and 3, 5 and 3, the x component of that's going to cancel out, and we're going to be left with a final vector going straight down. So, but they don't care about the direction. They care about the magnitude. So that's the concept of what's going on. That's why I kind of draw a picture when I always start. So we're going to find the big thing with electric field as opposed to electric potential is their vectors. So the equation for an electric field of a point charge is kq, there's just one q because there's just an electric field, over r squared. When you have force, then you have two q's. So force equals qv cross b plus qe vector, vector, vector. If you have force, then you have two q's, one q, two q. When you have just electric field on its own, then you have just one q. So that's important to note. Okay, so this is going to be a direction. I'm going to start by finding this one. So I'm going to look at the picture like so. Running out of colors. Well, not running out of colors. Running out of colors that I enjoy using. So we have an electric field going this direction. There we go. And this is going to be from the +4. And I can break this down to components. I'll call this EX. Nope, that should be EY because it's vertical. There we go. EY, EX, and these will be vectors. Oh, there we go. And since these are symmetrical, the 4s, the -4 and the +4 charges, it all symmetrical, so the EX components are going to cancel out. So all I want to do is find the EY component here, and we'll just go with that. So we'll start by finding this large magnetic field right here, or electric field, and this will be K, which is Coulomb's constant, 8.99 times 10 to the 9th. I'm going to use 9, just because it's convenient. We have 4 nanocoulombs, so we have 4 times 10 to the -9th coulombs, which is convenient because it cancels, nano for n, all over r squared. So now we need to find out what this radius here is. So we have it's 5 down and 3 over. So that is then going to be, let's see here. So that's 0.05 squared plus 0.03 squared. And then we're going to have to use a hypotenuse. So we square root everything. I'm going to rewrite this as 5 times 10 to the negative second plus 5 times 10 to the negative second. Then we square these. Square root. I'm terrible at this. So we're going to have, oh, that's supposed to be a 3. So 5 squared is 25. 3 squared is 9. So what we're going to end up with is square root of 34 centimeters. Oh, square root of 34 centimeters. Yep. So I'm just going to, and then that's going to be times 10 to the negative second. This way I keep everything in meters. So this is going to be, this will, oh, wait a second, because we're looking for r squared. So r squared would be 5 squared plus, sorry. So we don't have to square root everything, so we can square it all. So this will be 34 times 10 to the negative fourth. A little bit confusing. I'm sorry. So 0.05, 0.03, square this, and we get square root of, we get, let's see here, 34 times 10 to the negative fourth. So because this is the same as 5 times 10 to the negative second, square both sides, 3 times 10 to the negative second, square both of these. So we have 25 times 10 to the negative fourth, 9 times 10 to the negative fourth, add them together, and this is what we get. I am terrible at doing the Pythagorean theorem and being in any way comprehensible while doing it. Okay, so faith, yes, true, correct? Okay, good. So that's the distance here. That's supposed to be the easy part of this problem. Okay, so now that we have the electric field at this point, so we'll cancel some things out. So this will be 36 over 34 times 10 to the fourth. That is the electric field at that point. I'm going to rewrite this slightly as 18 over 17 times 10 to the fourth. And that's the electric field. Electric field is measured in, I think, newtons per coulomb. Yep, I think that's correct. So now we need to find just the y component of this. So if this is theta, and let's see, this is 5. I'm pretty sure that's 5. Yep, 5 and 3. Then we can find the angle of that. So we want cosine of theta. So cosine of theta equals, this will be square root of 34. Cosine of theta equals, so adjacent over hypotenuse. So adjacent will be 5. Hypotenuse will be square root of 34. And so, therefore, if we're doing this electric field times cosine of theta to get this portion right here, then we would have the E in the y direction equals 18 over 17 times 10 to the fourth times 5 over square root of 34. And that gives us just one of them. But if we want the total, the combined value of them, I'll write EY total, because this is from both, they're symmetrical, so I'm just doubling. This is from the 4 nanocoulombs and negative 4 nanocoulombs. We're going to multiply by 2. So we'll do 18 times, I'll write this out. I should write this out. Times 5 over 17, square root of 34, times 10 to the fourth. I'm going to see what our answer is going to look like real quick. So we're looking for kilo, which is 10 to the third. So I'm going to do one more simplification, then go to the calculator. I have more faith with me being able to write things out than putting in things in the calculator. So I like to simplify as much as possible before I go to the calculator. So this will be 10. This will be 10 to the third, and then another 10 right here. So I have 18 times 100 over 17 times the square root of 34. And then I'll leave this 10 to the third there because we know it's going to be kilo. And this will be newtons per coulomb. So go to the calculator. On clear 1800, that's 18 times 100, divided by 17, divided by quantity, second square root of 34. Get a couple more parentheses there. And this is 18.158. 18.158. And then this will be newtons per coulomb. Whoop, so messy. So messy. Copy that so I don't have to drag it. Paste it over here. And the answer then, I think, is going to probably be this guy, number E. I did a little bit of rounding. If I had to use 9 and I used 8.99 times 10 to the 9th for Coulomb's constant, it might have gotten me just low enough to get below that. I did some rounding somewhere. That's okay. So this is going to be the answer, 18.1. Oh, I forgot the K for kilo times 10 to the third newtons per coulomb. Backtrack, kind of see what we did here. We had, I'm going to erase these guys. Some of that. We had 3 particles. 1, 2, 3. It was symmetrical with respect to the x-axis, the top bottom. So the top particle provided an electric field going this direction. Bottom particle provided an electric field going that direction. But since these are both vectors, those are supposed to be little vector arrows, when they combine, they combine vectorially, as in components. You combine the x component, you combine the y component, using the Pythagorean theorem. They create then a total electric field going down like so. And that's what we were looking for with the cosine. And the equation for the electric field was kq over r squared. This is one of the differences between electric fields and potentials. Potentials are generally used for work and energy. Electric fields are generally used for force. The 2 big differences between electric field and potential is electric field has an r squared on the bottom, and it's a vector component, where potential, which has to do with energy, is a scalar. It is not a vector, and so you can just add them. Normally, you don't have to do the whole Pythagorean theorem components. So I hope that helped. I will see you next time.